Hi guys. So today we're going to look at some harder solving equations. And it's not that these first ones are harder, it's that these first ones really are a little bit uglier and going to take a little bit more work. So last class we saw some where if I had something like 1/3 to the x equals 3 to the x minus 1, I could rewrite 3 to have the same, or rewrite 1/3 to have the same base as 3 and find my answers. Well, sometimes we have a case like this one where I actually can't rewrite them with the same base. And what I also probably am not going to want to do is rewrite this as a log because it's going to get really messy because both of these have an exponent. Now, it's not saying you can't do that, but it does get a little bit ugly. So sometimes a different strategy that we want to use is we want to take the log of both sides. So what that means is we want to make whatever we have on each side the argument of a log. And as long as we do the same thing to both sides, we can do that. I can do log or I can do natural log. So I'll just do regular log. And what I'm going to do is I'm going to make 2 to the x and 3 to the x minus 1 the argument of that log. And the reason I'm doing that is because based off my properties, the x can move to the front and be multiplied, and I can take the x minus 1 and move it to the front and make it multiplied. Now what we're going to do at this step, we need to be careful that we understand what's happening. Log 3, remember, is an actual numerical answer. It's 10 to the something power. Okay, that actually is just an ugly decimal. So x minus 1 times log 3, I can actually distribute and rewrite as x times log 3 minus log 3. Because again, log 3 is just a single number. This is not the same thing as distributing a log to its argument. Okay, that's a very different thing. This is okay because again, we're taking the entire log. The entire log is still intact. We are not changing that argument here. Now the reason that we like to do that is because now we can use a similar strategy that we used when we did inverses for rationals. Let's get everything with an x on the same side of the equation. By doing that, that allows me to be able to factor out the x to get it by itself, and then I can divide by what's there. Now the thing about these types of questions, there are a lot of different correct ways to write your answer. What more than likely we're going to do is write an exact answer and then use a calculator to evaluate what it actually is. Now this is an acceptable exact answer. But again, there's different ways to write it. You can use your log properties and you could write the bottom as log of 2/3. You could rewrite the top as the log of 1/3. You can use change of base formula and write this as a single log. There's not one correct way to write it. There's a lot of different ways it'll work. So if your answer looks different but it gives you the same decimal, then that's okay. All right, let's try the next one. Same thing, I'm going to go ahead and take the log of both sides because there's no way to write 3 and 7 with the same base. Now I can take that exponent and move it to the front. And remember, by doing that, that means it's multiplied by what's there. So this is x log 3 plus 2 log 3. That's going to be x times log 7 minus log 7. Get everything with an x together. Put everything that doesn't have an x on the other side. Factor out your x so that you can divide by everything else. So again, your answer here is going to look a little ugly, and there is, again, more than one way to write your final answer. This is one form. Okay, that's not the only form, though. Again, if you type it in and you get an equivalent decimal, then your answer will work. All right, we're going to look at a couple more. A lot of what we're going to look at today are kind of some hidden factoring questions. So e to the 2x minus e to the x minus 6. So you may recognize here that you have something squared, something that's not squared, and something that's not there. This is actually factorable. Now, if you can't see it in its current form, you might want to substitute something. I'm going to let u take the place of e to the x. Well, that means e to the 2x would be u squared minus u minus 6. This is much easier to see that this is able to be factored. This factors into u minus 3 and u plus 2. So I get that u is 3 and u is negative 2. Again, remember though, we're not solving for u. Okay, we're solving for x. So I have to remember, if I do it this way, what I really have is that e to the x equals 3 and e to the x equals negative 2. So I do still have an additional step here to find x. Since the x is in the exponent, I'm going to have to rewrite this as a log. So remember, log base e is ln. So this would be the natural log of 3 is equal to x, and the natural log of negative 2 is equal to x. But again, natural log of negative 2, that's not possible. That's extraneous. You can't have a negative argument. So I only get one answer here. All right, let's try the next one. The next one looks really scary. But again, let's remember what we did last class. 1 over 16 can be rewritten with a base of 2. So this ugly thing is just an exponent. 1 over 16 is 2 to the negative 4. Well, now these have the same base. If they have the same base, then I can set those exponents equal to each other. Let's multiply both sides by log base 5 of x. Let's get the log by itself. So negative 1/2 is equal to log base 5 of x. So to figure out what that argument is, let's rewrite this in exponential form. So 5 to the negative 1/2 is equal to x. What 5 to the negative 1/2 means, it's 1 over the square root of 5. But we don't want square roots in the denominator, so let's rationalize and make it root 5 over 5. All right, these next two are also hidden factoring questions. They are hidden factoring questions. So again, it might be kind of hard to see in the current form, but let's recognize we have 5 to the x and 5 to the negative x. It might be easier for you if you rewrite it this way, because a negative exponent, remember, would move that to the bottom. It does not move the 3, it would just move the 5 to the x. So it doesn't look like it's quadratic right now, but what if I multiply this entire thing by 5 to the x? Well, 5 to the x times 5 to the x would be 5 to the 2x. That would cancel out that denominator here and make this 2 times 5 to the x. Well, now let's find a variable to replace it to make it a little bit easier. So this would be u squared equals 3 plus 2u. And this is a much less intimidating question to be able to factor. So at this point, we can factor and make this u minus 3 and u plus 1. I get that u is 3 and u is negative 1. But again, we're not solving for u, so 5 to the x equals 3 and 5 to the x equals negative 1. So our last step here would be to rewrite these as a log. So log base 5 of 3 is one answer over here, and log base 5 of negative 1. But we know you can't have a negative argument. So that's my answer. All right, this one, like I said, it is kind of a factoring question. So see if you can set this one up. Pause the video, try this one on your own. All right, what I'm going to do here, I'm going to rewrite 4 as 2 to the 2x. And like I told you guys, this is a factoring question. Since it's a factoring question, I'm going to let u be 2 to the x. So this would be u squared minus 2u minus 12. That's going to factor into u. Sorry, guys. That's not going to factor because I made a mistake. So that is 2 to the x. That's just regular old u. There we go. That makes more sense. Now this is going to factor into u minus 4 and u plus 3. So I get that u is 4, and I get that u is negative 3. But again, not solving for u. 2 to the x equals 4. 2 to the x equals negative 3. 2 to the x equals 4. We could rewrite this as a log, but we don't need to. We know what x is here. X has to be 2. If you tried to write this next one as a log, you again would notice you get a negative argument. So that one does not give you any answers. All right, so the last thing we're going to do is we're going to revisit some of these word problems. And what we're going to do now, we actually know the algebra how to solve some of these. So instead of just straight up using the calculator, we're actually going to show the algebra that we can use to actually find our answers. So the first one's a half-life example. It says the half-life of a radioactive element is 40 days. So remember in that formula, the bottom part of the exponent is the actual half-life. You start with 200 grams. After how many days would you be left with 75 grams? So I would set this up. 75 is the amount after time, 200 is the initial, 1/2 because it's half-life. We don't know the time, we do know the half-life. So in order to solve this, let's get the exponent base by itself. So we'll divide by 200. And again, we're going to find the exact answer here without plugging this into our calculator. So we write this as a log. Log base 1/2 of 75 over 200 equals x over 40. So to get x by itself, I would multiply both sides by 40. So this would be your exact answer. But at this point, you would go ahead and use a calculator, actually plug that in, and you're going to get the same answer you would as if you graphed that original question and did an xcal option. It's going to give you that same decimal. And that should be, let me find my 56.6 days. And again, with half-life, you can make sure your answer is reasonable. Okay, it's going to be more than one half-life to get down to 75, but not as much as two, because one half-life would put me at 100, another half-life would put me at 50. So somewhere between 1 and 2 half-lives, so somewhere between 40 and 80. Okay, it's reasonable. It makes sense. All right, next one. The number of bacteria in a culture, culturally, that's interesting, that should say culture, is growing at a continuous rate. The number of bacteria increases from 600 to 1,800 in 5 hours. So it triples every 5 hours. We want to know how many bacteria there will be after 12 hours. So if it triples every 5 hours, then I can set this up. Here's my original. Then I can do, this is 3. It's every 5 hours. So we want to know after 12 hours, 12 divided by 5. This one actually is not going to require any algebra unless you wanted to work backwards to find the rate. But if we know it's tripling every 5 hours, then we can set it up this way. Plug that into a calculator. We get 8,380 bacteria. All right. On this next one, compound interest. Compounded continuously. Remember what that phrase means. $5,000, 1.25% interest compounding continuously. How long will it take for the account to have $5,500? So we would do 5,500 equals 5,000 E. 1.25% is a decimal, 0.0125. And we want to know how long, so that's my x. So divide by 5,000, that's going to be 55 over 50, which I'm just going to write as 11 over 10. The base at this point is by itself. Let's rewrite it as a log. Log base E is ln. So natural log of 11 over 10 equals 0.0125x. Divide by 0.0125. At this point, that is your exact answer. Plug that into a calculator, and you'll get your actual answer of 0.7625 years. So these last ones actually don't require any algebra to figure out, but these are some examples of some log-based things that you may see. There's a lot of things in the real world that have a log-based scale. The Richter system, a Richter scale, the decibel system for measuring sound. Because it's the inverse of an exponential, log-based can be used for a lot of these things. And there's a few more examples like that on your practice. One you may have seen in chemistry is the formula for pH. pH is negative log of the hydrogen ion concentration in moles per liter. So hopefully you learned this in chemistry already. If not, we're a little early. But if the pH is less than 7, then it's acidic. If it's greater than 7, then it's basic. So this tells you the hydrogen ion concentration of apple juice. So if I want to find the pH, I would just do negative log of 0.0003. This is a straight up calculator computation. Plug that in, you're going to get 3.523. But using that information, that can tell us, since it's less than 7, apple juice is acidic. All right, this last one I just always thought was kind of interesting. There was actually an article that my mom found that showed that the best way to convert from dog years to human years is not just +7. It's actually a log-based scale. It actually makes a lot of sense when you think about a puppy as they grow to be older. But we're not going to get into that. But using this scale, we can actually find a better conversion for the equivalent age of a 15-year-old dog. So if you were to plug this in, it tells you H is the human equivalent and D is the dog's age. We want to find the human age of a 15-year-old dog. Well, I would do 16 times the natural log of 15 plus 31. Again, this is just a straight-up calculator question. If you plug that in, you get 74.329 years. And if you think about it, I think that kind of makes a little bit more sense because a 15-year-old dog is pretty old. If I just do the +7 or times 7 or whatever it is they say, that might be a little bit too old than what the normal conversion would be. So I think this gives us a little bit more accurate of a conversion. All right, so that is it for our equations. Again, we really only have one more thing to do in this unit, and that is going to be graphs and inverses.